Hi everyone, welcome to the review session for the first exam, which will cover material from chapters 1 and 2. This video will step you through a dozen different problems, beginning with set theory from chapter 1, section C, and ending with word problems involving conversions of units from chapter 2, section B. Let's go ahead and get started. Number 1, use set notation to write the members of the following set, or state that the set has no members. The perfect squares between 8 and 26. So if we're looking for squared values, let's first just kind of figure out what might those values be. We have 1 squared, that's 1, 2 squared, 4, 3 squared, 9, 4 squared, 16, 5 squared, 25, 6 squared, 36, 7 squared, 49, so on and so forth. So 1, 4, 9, 16, 25, 36, 49, those are all perfect squares. They are the squared value of something else. So if I'm looking for the set of values between 8 and 26 that are all perfect squares, first of all I'm going to start with my proper set notation, that is to open with a brace, and then to list the members separating them by commas. So strictly between 8 and 26, that would be 9, 16, and 25. There are 3 members of this set. I'm going to close the set with the other brace. Number 2, consider the sets of natural numbers, whole numbers, integers, rational numbers, and real numbers. Identify from the list above the first set that describes the given number. Okay, so this might be a good opportunity just to review what all of these sets of numbers look like. So the smallest set is the set of natural numbers, which we use kind of a interesting looking uppercase N to denote that set. This is simply the set of counting numbers, so 1, 2, 3, so on and so forth. We also have the set of whole numbers, which we find by just adding one element to the set of natural numbers, and that element is the number 0. So if we add 0 to the set of counting numbers, we get the set of whole numbers. The next largest set is the set of integers, which we use the uppercase Z for. This is the set of all whole numbers plus opposites of the natural numbers. So we're going to use ellipses to denote that these values are continuing on and on for all negative values. -3, -2, -1, 0, 1, 2, and 3. And so on and so forth in both directions. All right, now at this point we're ready to talk about the set of rational numbers, which the root word there meaning ratio. So this is the set of all values that can be written as a fraction or ratio of integers. So since there's really no logical place to start listing values of the rational numbers, we have to use what's called set builder notation. So the symbolism for the rational numbers is Q. And again, I can't really start with a fraction and assume that my reader or whoever is considering this set, that they're going to understand what I mean by any kind of pattern of ratios. So I have to say this is the set of all elements such that those elements can be written as a ratio of integers. So where m and n are integers, and in particular, n cannot be 0. Because if n is 0, I would have essentially a division problem with 0 as the divisor, and we know that that is undefined. So n can be any value, m can be any value, positive or negative, integer-wise, but n cannot be 0. So this is the set of all things that can be written in fraction form. Obviously, any real number that cannot be written in fraction form would be said to be irrational. So values that do not fall in the set of rational numbers are irrational numbers. And this is obviously the set of all things such that those things cannot be written as a ratio of integers. So where m and n, again, are integers, n is not 0. So the set of all things that are not rational numbers. Okay, together, these two last sets that we have written here, the rational numbers and the irrational numbers, together they make up the set of real numbers. So that is our last defined set here. The real numbers are a union of rationals and irrationals. In class, we did kind of a subset visualization of all the relationships between these sets by using concentric circles and then a box to contain the Venn diagram. So, for example, we said that smallest set was the set of natural numbers. Adding one element to that set gave us the set of whole numbers. Adding one element to that set gave us, I'm sorry, not one element, but adding all of the negative natural numbers to this set gave us the set of integers. And then making fractions of those integers, positive and negative, gave us the set of rational numbers. And adding, that's not going to work, is it? Adding the irrational numbers to the rational numbers in union gave us all of the real numbers together. So the irrational numbers are kind of in this tube shape outside of the set of rational numbers. So they are separate from each other. Now, we know that there are other number systems outside of the set of real numbers. So we encase all this in a box to denote those values that are non-real. So those are the imaginary numbers, which is part of the complex number system. So we would say that the relationship here, this is a subset idea. Once you leave the smaller circle, you're in a bigger circle and more elements are available to you. So if we are trying to find the first set that is going to hold the element negative 7/8, it's obviously not a counting number, not a whole number, not an integer, but it is a rational number. So we would say that negative 7/8 is in the set of rational numbers. Negative 7/8 is a rational number. And since it is inside also the set of real numbers, we say it is negative 7/8 is also a real number. But the first set that would contain it would be the set of rational numbers. All right, number 3. Patients in a hospital on a single day were taking antibiotics A, blood pressure medication BP, pain medication P, in numbers summarized in the table. Draw a 3-circle Venn diagram that summarizes the results in the table. Okay, so since we have all 3 of these things individually, a category denoting none of them, and a category denoting all of them, plus paired combinations, I would say that this would look like 3 interlocking circles. 3 interlocking circles. So 1 for antibiotics, 1 for blood pressure medication, and 1 for pain. Now, to denote those elements that are not in any of those 3 categories, of course, we need to put the whole thing in a box and then fill in our values. So there would be 18 here and 6 here, 21 here, 5 outside. Antibiotics and blood pressure only, 10. Antibiotics and pain only, 27. Blood pressure and pain, 10. And all 3 right in the middle here, 25. Okay, so number 4, how many patients took blood pressure medication but not pain medication? Blood pressure but not pain. Let's see. This is my blood pressure circle, but I want to exclude those that took pain medication. So at least taking blood pressure medication, which put you in this crescent area here. So I would say 10 plus 6, 16 people. All right, number 5. Number 5 introduces us into section D of chapter 1, where we talked about analyzing different types of arguments, and the 2 that we focused on were inductive and deductive arguments. Just as a quick recap, inductive arguments were arguments that relied solely on examples. So inductive arguments were example-based. And we would recall that they are the type of arguments that cannot be proven. They are analyzed based off of their examples. So we would either say there are strong inductive arguments or weak inductive arguments, just based off of what is stated in the premises. So kind of a generic definition for an inductive argument is one that begins with very specific premises and ends with a generalized conclusion that kind of encompasses, again, a general statement about all of the examples that are listed. On the flip side, a deductive argument begins with very generalized statements and ends with a very specific conclusion. So let's just make a quick note about that. Inductive arguments start with specific, I hope I spelled that right, specific examples and ends with a very generalized conclusion that encompasses all of those specified examples. And a deductive argument can be proven since it starts general and ends specific. Now, a deductive argument, to analyze it, we rely on essentially two levels. The first level is what we call the test for validity, and this is a process where we draw a Venn diagram based solely off of what the argument presents to us in the premises, and then we compare that argument, that Venn diagram setup, to the conclusion. And if the conclusion matches our picture, we say that the argument has the correct structure, in which case the conclusion follows necessarily from the premises, and that is what we call a valid argument. Now, if the premises are also true, then that is our highest level of a deductive argument. That is when we call it sound. So when it is valid and all the premises are true, that's really the best argument that we can possibly have, a sound argument. So what we have here in the example is a deductive argument. We start with very general statements and we conclude with a very specific conclusion here. So premise 1 says, if you live in Cleveland, then you live in Ohio. Premise 2 says, Amanda does not live in Cleveland. The conclusion is that Amanda does not live in Ohio. So our first task is to use the test for validity. So we're going to draw a Venn diagram and see if it matches our conclusion. So the test for validity is, again, just to see if the overall structure is there in the argument, that this conclusion would follow necessarily from what is stated in the premises. So premise 1 helps us set up the relationship of all the sets. Premise 2 is what draws the X. And then again, we compare that Venn diagram to the conclusion. If they match, the argument is said to be valid. So in premise 1, if you live in Cleveland, then you live in Ohio. It's already in the if P then Q form, so I'm not really worried about putting it in the correct conditional format. But another way that you can think about these conditional statements is to put them in the subject-predicate form. If you live in Cleveland, then you live in Ohio. Another way to say that is that all people who live in Cleveland, all people who live in Cleveland live in Ohio. So all SRP, all Clevelandites are also residents of Ohio. So this first premise really sets up a subset kind of notation for us, where the innermost circle is those folks who live in Cleveland. All people who live in Cleveland live in Ohio. Okay. Premise 2 says Amanda does not live in Cleveland. So I first need to finish my picture here to denote all folks who do not live in Ohio, right? Those would be the ones outside of the circle. Premise 2, if Amanda does not live in Cleveland, I cannot assume that she lives in Ohio. So In other words, I want to make sure that I'm outside of the living in Cleveland circle, but not necessarily in or outside of the living in Ohio circle. I can't assume one way or the other because the argument does not specifically state it. So at best, I can put the X on the border. The conclusion is Amanda does not live in Ohio. Well, that conclusion does not match our picture. The only way it would match is if this X was specifically outside of the living in Ohio circle, and it's not. So because our picture does not match our conclusion, we say that this argument is invalid. It does not have the structure such that this conclusion follows necessarily from what the premises are saying, right? Even though the premises are true, right? If you live in Cleveland, then obviously you live in Ohio. Cleveland is a city in Ohio. Amanda does not live in Cleveland. That's just a statement of fact. So even though the premises are true, we can still have an invalid argument. And because it's invalid, we can also say that this argument is not sound, right? Because we need both validity and true premises to make a sound argument, and we're missing the structure here. Okay, let's talk a little bit more about inductive and deductive arguments. Explain whether the following argument is deductive or inductive. The Flanagans are having their 6th child. All of their children are musically gifted. So the youngest child is bound to be musically gifted as well. Okay, so we said that an inductive argument was based off of examples, specific examples that led to a very generalized conclusion that kind of encompassed all of the details and all the characteristics of the examples. A deductive argument was one that began with very general statements and led to a specific conclusion, which is what I believe is happening here. There are no examples going on that are leading to something generalized. We have very general beginning statements. The Flanagans are having their 6th kid. All their children are musically gifted. Now we're leading to the specific conclusion that the youngest child, the child they're about to have, the 6th child, is bound to be musically gifted as well, right? General statements leading to a very specific conclusion. The youngest kid is going to be musically gifted too. So I would say that this is a deductive argument. Now, obviously, we need an example of an inductive argument, so this is really what's happening in number 7. Explain whether the following argument is deductive or inductive. Premise 1, -7 times -4 is 28. Premise 2, -2 times -7 is positive 14. Premise 3, -3 times -5 is positive 15. And the conclusion, when two negative numbers are multiplied, the result is a positive number. This is a very clear setup of an inductive argument. Why? Because the premises themselves are very specific examples, right? I didn't utilize all possible negative integers, right? There's only 3 listed here, and in fact, they are all single-digit negative integers. But I have very specific examples, and I'm trying to use those examples to build a case for my generalized conclusion, right? 2 negative numbers are multiplied, the result is a positive number. That is a general statement that kind of encompasses all of the detail and the characteristics of the examples that are in my premises. So this is a setup for an inductive argument. All right, in number 8, we are starting to breach into the material that's covered in chapter 2, where we start working with conversion factors. So number 8 reads, 1 cubic foot holds 7.48 gallons of water, and 1 gallon of water weighs 8.33 pounds. The question is, how much does 7.5 cubic feet of water weigh in pounds? Round to 1 decimal place. So what they're asking us to do here is to convert 7.5 cubic feet into pounds. The first step for us is always to begin with that given information just by writing a ratio. So 7.5 cubic feet, we want to turn this into pounds. Now, what's told to me is the connection from cubic feet to gallons, and then from gallons to pounds. So in total, I'm going to have 2 conversion ratios here by the time I'm done. One to transform cubic feet into gallons. Notice my setup here, numerators and cross denominators will cancel. And then gallons into pounds. Gallons will cancel. And we're left with the unit that the problem wants the water's measurement to be converted into, right? So I have my units already set up so that I am ending with the unit that the problem wants. So now I'm going to go back in and fill in the values. 1 cubic foot holds 7.48 gallons, and 1 gallon of water weighs 8.33 pounds. Now, conveniently, my denominators are 1, so when I multiply across numerators and across denominators, I don't have to worry about dividing at the end, right? Because divided by 1 isn't going to change anything. So I can just multiply across the numerators here, 7.5 times 7.48 times 8.33, and that's going to give me a total of 467.3 pounds. All right. Number 9. We want to convert the following temperatures from Fahrenheit to Celsius or vice versa and round to 1 decimal place. So we want to transform 40 degrees into degrees Celsius, and we want to transform 45 degrees Celsius into degrees Fahrenheit. Now, to complete this problem, we're going to need those formulas from the back of the conversion charts. So let's go ahead and write those down first. So what's nice about these temperature conversion problems is that they're really just plug and chug type of problems. So the value F here, we're just going to plug in 40, and the value C, we're going to plug in 45. So we've got 40 minus 32 over 1.8. Order of operations says that we have to do this difference first before we divide. And here we're going to plug in 1.8 times 45 plus 32. So 40 degrees Fahrenheit is equal to 4.4 degrees Celsius. And 45 degrees Celsius is equal to 113 degrees Fahrenheit. Number 10, we want to convert 315 cubic inches to cubic centimeters, round to the nearest hundredth. Okay, so there are 2 things I really want to make mention of in this problem. Number 1, we are working in a higher dimension than the values listed on our conversion chart. All of those values are in the first degree. They're in the first dimension, meaning that most of them, if we're talking about length, there's no exponents on any of our units. In this problem, we're talking about cubic units. So here, we're in the third dimension, we're talking about volume. So we want to make sure that our conversion ratios reflect the fact that we are now in a different dimension. Also, inches and centimeters are different measurement systems. Inches is part of the U.S. customary system. Centimeters is part of the metric system. So we want to be looking at the table at the bottom of our conversion sheets that is converting between systems, not within systems, but between systems. And then also reflect the fact that we are in a higher dimension by cubing all of our units of measure. Okay. So again, to start with, I'm going to put the given information, 315 cubic inches over 1, and then set up my conversion ratios to reduce this unit. So I want to end in cubic centimeters. Now, while I don't have a direct connection between cubic inches and cubic centimeters, I do have a connection between inches and centimeters. According to my chart, 1 inch is equal to 2.54 centimeters. Okay, so at the very least, I have inches to centimeters. 1 inch is 2.54 centimeters. Now, if I left it like this, I would not have a true cancellation going on between my cubic inches and just inches, right? Because let's just take a detour here real quick. Inches cubed over inches, which is what I've got going on here. Inches cubed over inches. This is inch times inch times inch over inch to the first degree. I would only be reducing 1 power on this unit if I left it as inches to the first degree. I would still have inches squared in the numerator if I left the conversion factor like this. In order to have a true cancellation between cubic inches and inches to the first degree, I need to cube this entire ratio, right? Because I can't just pick a part of the fraction to raise to a power. If I'm going from linear units to cubic units to something that is involved in volume, then I need to raise the power on both of these things, right? Because this is a statement of equality. 2.54 centimeters is equal to 1 inch, right? This is not just multiplying by 2.54. This whole statement here is a statement of equality. This value is essentially 1, right? Because these two quantities are the same. So if I want to cancel out this inches cubed unit here, I really need to cube this whole thing. So in other words, what I've got going on is 315 cubic inches times whatever 2.54 cubed is in cubic centimeters to 1 cubic inch, right? 1 times 1 times 1 is still 1, so the denominator isn't changing for us. But because we're cubing this entire factor, right, we're cubing this entire conversion ratio here, it's cubing the inches unit and it's also cubing the centimeters unit. So now I have centimeters cubed to centimeters, or centimeters cubed to inches cubed. So let's also make a mental note here that this notation does not mean 2.54 times 3. It means 3 factors of 2.54. So this value times itself 3 times. So in our calculators, you can use the exponent button to cube the 2.54, or you could literally just type 2.54 times 2.54 times 2.54 times 315. In total, right, these units are now ready to cancel. We have 5,161.93 cubic centimeters. And that is rounded to the nearest hundredth. Almost done. 2 more problems here. Assume that when you take a bath, you fill a tub to the halfway point. The tub measures 6 feet by 3 feet by 2.3 feet. When you take a shower, you use a shower head with a flow rate of 1.98 gallons per minute, and you typically spend 7 minutes in the shower. Assume there are 7.5 gallons in 1 cubic foot. Do you use more water taking a shower or taking a bath? What is the absolute difference in gallons? Oh, this is a great problem. Okay. So I really have 2 instances going on here, right? I could be taking a bath, or I could be taking a shower, and I want to compare which one uses more water. So in essence, I want to find out the total number of gallons that are used by taking a bath, the total number of gallons used by taking a shower, and then compare those 2 numbers. So let's start with the bathtub. When you take a bath, you fill a tub to the halfway point. And then it gives you the dimensions of the tub. So we're going to assume that that's a rectangular prism and measure the volume of that tub by length times width times height. So again, forgive my drawing abilities, but we're going to assume that this is our tub, and we've got 6 feet by 2.3 feet by 3 feet, so length times width times height. The volume of our tub is going to be the product of all 3 of those values, length times width times height. So that's going to give us a total volume, if we filled that tub up to the very brim, of 41.4 cubic feet. Notice how I got that unit, right? Each one of these dimensions was given to us in feet. So if I multiply feet by feet by feet, I'm going to have cubic feet in terms of volume. Now, the problem also dictates that we fill a tub to the halfway point. So I'm really, when taking a bath, I'm really only using half of this. So let's take the time right now just to divide that in half. So that's 20.7 cubic feet of water. 20.7 cubic feet of water. Okay, now in order to make a direct comparison between the amount of water used in the bathtub and the amount of water used in the shower, I really should transform this into gallons. So let's take our information now and put it into the comparable unit. So cubic feet up here. I want to get rid of it by putting in the denominator down here, and I want to turn it into gallons. So in the problem, it tells us assume there are 7.5 gallons in 1 cubic foot. In 1 cubic foot, there are 7.5 gallons. So we're going to take 20.7 and multiply that by 7.5. So in total, taking a bath, we are using 155.25 gallons. All right, now let's move to the shower. Let's see. The flow rate of the shower is 1.98 gallons per minute. 1.98 gallons per every 1 minute. And you take a 7-minute shower. 7 minutes. How many gallons is that going to be? 1.98 times 7 is 13.86. That's a very quick shower. I don't think I've ever showered in 7 minutes. Okay, so obviously we're going to use a lot more water taking a bath. So let's find the absolute difference in this amount. So we're going to do 155.25, and we are going to subtract the 13.86. 155.25 subtract 13.86. That is an absolute difference of 141.39 gallons. 141.39 gallons. All right, let's do one more problem together. Decide which of the two given prices is the better deal and explain why. Okay, so price comparison based off of quantity. You can buy shampoo in a 6-ounce bottle for $3.49 or in a 14-ounce bottle for $9.79. Okay, so a little bit over double the amount of the first shampoo bottle. And it's about twice the price. So which one is really the better deal? Do you buy several of the 6-ounce bottles or one of the 14-ounce bottles? Okay, so to do these type of which is the better deal type problems, we really need to put both of these quantities in the same unit of measure. Now they're both in terms of ounces, right, but different size ounce bottles. So 6-ounce versus 14-ounce. Really one way to think about this is let's put them both into per pound type quantities. So we've got one bottle that is $3.49 per 6 ounces. Oops. I know that there are 16 ounces in 1 pound. So I could transform this quantity into the price per pound. And I could do the same thing for the 14-ounce bottle. It is $9.79 for a 14-ounce bottle. If I transform this into price per pound, I can very easily then compare these two shampoo bottles. So in the numerator here, the ounces are going to cross cancel, same here. We'll be left with money per pound. So multiplying across the numerator, we've got 3.49 times 16. And we're going to divide that by 6 to get our price per pound. And in this quantity, we're going to take 9.79 and multiply that by 16, and then divide it by 14 to again get a price per pound. So in the first ratio, if we do 3.49 times 16, that's 55.84. Divide that by 6. That's about $9.31 per pound, or equivalently about 58 cents per ounce. Now in the second bottle, we're going to do 9.79, multiply that by 16, and then divide by 14. And that's going to give us about $11.19 per pound, or equivalently about 70 cents per ounce. Okay, so actually the smaller shampoo, the 6-ounce bottle for $3.49 is the better deal, because the cost per ounce is only 58 cents, while the 14-ounce bottle is approximately 70 cents per ounce. So our 6-ounce bottle for $3.49 is our better deal. All right, those are all the review problems I have for you right now. Obviously, this test does not cover every single problem I could potentially ask on the exam, but it gives you a rough idea about the level of difficulty, and we are going to cover basically all of the concepts. So again, feel free to study those definitions, write down solution kind of process and steps on your formula sheet, and be ready to answer questions from the 2 sections in Chapter 1, Sections C and D, and Sections A and B of Chapter 2.